In the last video, we took a look at a specific logarithmic graph. We took a look at the graph y equals log base 2 of x. But now we want to generalize this, and we want to talk about what if instead of only looking at log base 2, we look at log base a. So let's begin by talking about the idea of asymptotes. Graphs of functions like y equals log base a of x are always going to have a vertical asymptote at x equals 0, only approached from the right. And this corresponds to the horizontal asymptote that every graph like y equals a to the x has at y equals 0, when it's only approached from above. So this all kind of ties back to the fact that this is the inverse of that exponential function. So you'll see a relationship between these general properties of logarithmic graphs and the general properties of exponential graphs. I recommend you have both of these related pages open at the same time and just kind of compare the two of them. So the domain of y equals log base a of x, and remember a has to be greater than 1 in order for this to make any sense here for this particular graph. Then we're looking at x is greater than 0, which in interval notation looks like 0 to infinity. The range is all real numbers, which in interval notation is negative infinity to infinity. The x-intercept is happening at 1, 0, which is the inverse of the y-intercept for that exponential function. And if we walk along this function from left to right, we notice that we're going up, so therefore this is increasing for all real numbers. This is 1-to-1 because it passes the horizontal and vertical line test, and in fact we know that its inverse is y equals a to the x. It has a vertical asymptote at x equals 0, so it's going to approach this line, but it will never reach or cross it. And it is continuous because I can informally talk about continuity as I can draw it without picking up my pencil. So just remember that this is a reflection of the exponential function y equals a to the x in the line y equals x. Now that we've talked about logarithmic graphs in general, we want to do the same thing that we were doing with exponential functions, where we bring in everything that we were studying in sections 1.6 and 1.7 with transformations, so that we can look at a logarithm as a transformation of the parent function. So we need to be able to identify what the parent function is. In this case, the parent function would be y equals log base 5 of x. And now this one is being shifted horizontally left 7 and down 3, which means that if I can come up with a nice graph of log base 5 of x, I can shift each ordered pair left 7 and down 3 to create the graph of this transformed function. For part B, the parent function is y equals log of x. And so what I do is I take this function, and this negative inside the argument indicates that I'm going to do a horizontal reflection, which means that I'm going to do a reflection over the y-axis, and then the 2 on the outside is going to indicate that I'm doing a vertical stretch by a factor of 2. And I just want to note that when you do shift a logarithmic graph horizontally, that's going to change its domain. So when we were talking about the domain always is x is greater than 0, that's assuming it's that non-shifted function, that it's just log base, some number greater than 1 to log base something greater than 1 of x. It's nothing like what I have in this example on the screen right now. So that's the end of this page. As we continue into the next video, we're going to start talking about the natural logarithmic function. You may want to pause this and just go back and review the part of the video in 3.1 where you talk about e and the natural exponential function, because these two are, of course, completely tied to each other. So review that, and then come back and you can build on that knowledge to understand the natural logarithmic function.